Hello, and thank you for joining this webinar. This is the fourth webinar in our sustainability-focused webinar series. In the three previous webinars, we talked about the regulation of sustainability, dove into the digital product passport, and explored the sustainability perspective when developing products. One of the main takeaways was the importance of measuring sustainability to make informed decisions. Today, we will take a closer look at one of the methods that is being applied to quantify the environmental performance of products. This is the lifecycle assessment and how it can be used in product development. For any new attendees, my name is Mikkel, and I'm an engineer here at Gradis who's working with sustainability in product development. In some of my projects, I have worked with implementing recycled plastics in R&D, performed lifecycle assessments to measure the carbon footprint and identifying improvement opportunities in products, and I've been developing tools that can measure circularity as a parameter in the product development process. Today, I'll give a quick introduction to the lifecycle assessment methodology, what it is, what you can use it for, and an insight into how an LCA is conducted. As data is a key element in LCAs, I will also be talking about what data you'll need and where you can get it from. Then I will also give some input to how you can implement LCA into your product development to inform your product design and provide documentation of your final product. And lastly, I'll give some pointers to get started with LCA in your company. Let's start with a brief introduction. The core principle of the lifecycle assessment is, as the name suggests, the product lifecycle. I've illustrated the lifecycle of a product that starts with extracting the raw materials for the product, manufacturing them into specific parts, transporting them to the use phase, where they can be used until they reach the end of lifetime, and are recycled or become waste after the use phase. The LCA is a method that is used to evaluate the environmental impacts of a product by taking into account all processes throughout all phases of the product lifecycle. Being an assessment methodology, the LCA can have different scopes depending on what you want to assess. Sometimes the scope only includes the production of the product, which is called cradle to gate. That's the gate of the customer. Most often, the entire lifecycle is included, making it a cradle to grave because the product becomes waste. Increasingly, the link between end of life and raw material input, which is the recycling phase, is also included, which makes this a cradle to cradle LCA. LCAs are often conducted once the product is made to document the environmental impacts of the product. This can be used to provide customers with a carbon footprint. It can be used as marketing material or to comply with regulations such as documented your Scope 3 emissions. But to get the most out of an LCA, the insights you get could be used as input to decision making. For example, to guide a redesign to reduce the environmental impacts of your product. To make an LCA, you're going to need a lot of information about the lifecycle of your product, such as which raw materials are used for the manufacturing, where do they come from, how is the product processed during manufacturing, how much waste is produced, how is the product transported, is it by truck, is it by ship, is it by airplane, how is it used and for how long, what happens at the end of life, which we'll get into in a moment. The LCA is a methodology, it's a structured approach, and it does have limitations. It is used to measure the environmental impact of the product in focus, but the result is only as certain as the data being input into this methodology. It cannot be used to answer if your product is sustainable. It can only provide a relative answer. For example, which of the two concepts have a lower carbon footprint, and that answer is dependent on the scope of your assessment also. One electric car might have a higher production footprint than the fossil alternative if we look only at the production phase, but a lower footprint in the overall life cycle when including the use phase. This is just an example. An LCA can be used to highlight hotspots, where the large impacts are in the product life cycle, which is where there is the highest potential to reduce the impacts. But since the results are based on existing data, it cannot predict the future impacts directly. The LCA gives insight into the life cycle and creates transparency that supports decision-making. But it only includes the environmental sustainability aspect. It does not take into account the economical perspective or whether your production is socially responsible. Lastly, the LCA facilitates comparisons, but the accuracy of the result depends on your input data and also the scope of your study. Let's take a closer look at how an LCA is performed. The LCA methodology is a standardized process following the ISO standards 1440 and 1444. This is to ensure consistency and transparency across the studies being conducted and ensuring that specific sections and content is in place within the LCA studies. The ISO 1440 standard provides the principles and framework for conducting an LCA, while the ISO 1444 standard provides requirements and guidelines. The International Reference Life Cycle Data System, also called the ILCD guidelines, are made by the European Commission based on the standards to provide detailed technical guidance for conducting LCAs. This includes comprehensive guidelines for goal and scope definition, data collection, assessment, and interpretation of results. The goal of the LCD guidelines are to enhance the consistency and quality of LCA studies aligned with the standards, and it's also available for free on the web, so you can use it as guidance. One of the things that are outlined in the standards and the LCD guidelines is the process of an LCA. The first phase of an LCA is the goal and scope definition. This phase defines what will be assessed and why, to what extent, the methodological choice, etc. This is the foundation for the whole assessment and will greatly influence what data is gathered and also the results in the end. If we take a closer look at this phase, one of the things that have to be defined in the scope of this study is the functional unit. What is the functional unit? The results of an LCA are often used for comparison. But how do we compare products with different, for example, efficiency? If it takes twice the amount of one paint to cover the same amount of wall as another paint, then this efficiency difference must be factored in. Then stating that the carbon footprint of 1 liter of paint is being studied, it's not sufficient. Therefore, a common reference point must be established to make results meaningful and also interpretable. In this example for the paint, it's covering a specific amount of wall for a specific amount of time with a specific performance. These are the requirements to be able to compare to these results, and also what these paints will be scaled up to. Another thing that must be defined is the product system. In LCAs, your product is seen as a system of processes. It's all the processes that make up the life cycle of your product being assessed. Everything that is within your system of your product being assessed is within your system boundaries. And the product system is divided into a background system that contains processes that are more generic and a foreground system that contains all the processes that are specific to your product. This distinction is relevant to make when we get to the data in a moment, because you will need more specific data on your foreground system than you do for your background system. Once you know what to assess and how, the next phase in the lifecycle assessment is the inventory analysis. This is where the data is collected on all inputs and outputs of all the processes in your product system. And this is also the largest phase in most lifecycle assessments, because the better the data you collect, the higher the quality of your LCA's results will be. Once the data is collected, the product system is modeled in the LCA software, which calculates the environmental impacts according to the scope of your study and delivers a result. Usually this is also done during the inventory analysis to identify the gaps and also guide the data collection. The results are then interpreted by checking how sensitive they are to changes in the underlying assumptions, how uncertain the result is, and by drawing conclusions, limitations, and recommendations of the study. The study is then documented and may undergo a critical review by a third party. Let's take a look into how the product system is modeled in the LCA software. This example is a very simple example of a steel bracket. In the bill of materials, we have that this is one bracket of 9.14 kilograms of sheet metal. What we see from the CAD file is that it has 3 bends and some machining processes. This part is input into the LCA software as 9.14 kilos of a process that are made called plate steel machined bend. That includes the input of steel, that's the material input, and the manufacturing process input, which is the manufacturing of that steel. This is a very generic example, but I hope it gives you a little insight into how the product is modeled based on the input data. Once all the processes are modeled in the product system, we can begin calculating the impacts. What actually happens inside the software is that we have input all the inventory data. That's the data that we have gathered and we modeled our system. That includes specific amounts of substances being measured. The first process happening is the characterization. This is where the inventory data is converted into environmental impacts using these characterization factors. These factors are science-based For example, if a process emits 1 kilo of CO2 gas, then it might contribute to the climate change impact category and also the summer smog impact category in this example. These impact categories are called midpoint impacts and each have their own unique unit. For example, climate change is often measured in kilo CO2 equivalents. We call it equivalents because some other gases, such as methane, that's not CO2, does not equal 1 kilo of CO2. Methane is maybe around 25 times worse per kilo, depending on the methodology, which means that it is 25 kilo CO2 equivalent per kilo of methane. Some studies stop at midpoint, such as carbon footprint studies. But at midpoint, it's a lot of impact categories to consider. And these can be further grouped into endpoint impacts, such as damage to human health, damage to ecosystems, and resource scarcity. Some studies even continue to a single score, but all of these steps require some kind of weighting. How will you compare 1 kilo of climate change to some amount of human toxicity? You're comparing apples to oranges, which includes some weighting as to which is more important and is therefore more subjective. Another term is normalization, which is when the results are scaled to a common reference. It could be internally according to the highest score, or externally, for example, to one European person's yearly consumption. As we talked about previously, the results of an LCA are not absolute. So how will you know if 2 tons of CO2 equivalent is a lot or if it's not a lot? But this also depends on what you compare it to. So it's also viewed as being some degree of subjective. If we dive into the impact categories, these are some examples taken from the recipe methodology as an example. It includes various impacts that the emissions from our product system might have on the environment, such as climate change, which measures the potential contribution to global warming due to greenhouse gas emissions, which is expressed in CO2 equivalents. It can include ozone depletion, which assesses the potential for substances to deplete the stratospheric ozone layer. It includes toxicity, which evaluates the potential harm to human health from toxic substances. Includes resource depletion, which assesses the consumption of non-renewable resources. It also includes water use, which evaluates the potential impacts associated with the consumption of freshwater resources. These are just a few examples on how environmental impacts are measured inside a lifecycle assessment. Most often, when comparing products on these multiple different parameters, there will also be trade-offs between these. Maybe the carbon footprint of a cotton t-shirt is lower than a polyester t-shirt, but the water use is much higher from the cotton production. Which one is then more sustainable? That depends on what you prioritize when measuring this and also how it's used. In practice, the lifecycle assessment process will often look like this. You have the goal and scope of the study, and that's defined based on the objective of the study. This phase defines the target and also the plan for the LCA and includes the sections outlined from the standards. Then the data gathering begins with input of existing data, for example, from previous LCA studies, and specific data from maybe your product development. The suppliers in your supply chain are engaged, and also any data gaps are outlined and then also filled out. The data is then input into the lifecycle assessment software to model the product system, and then the product system is calculated into the environmental impacts. This process of these 3 steps of data collection, modeling, and also calculation are very iterative. The first results show any data gaps, and where in your product system specific data is especially important, which informs the next data gathering process and then the next calculation. It also includes assistance from internal stakeholders such as product management, sourcing, production, and also product development, and engagement of suppliers externally to get the required data. The study is then documented according to the standards and presented according to the scope of the study. For example, if there are any special requirements from marketing to the communication of the results. At the core of a lifecycle assessment, there is data. The results of your lifecycle assessment are only as good as the data you input. This is an example of the data need for a cradle-to-gate analysis. For the material extraction stage, you will need to know the specific materials used in your product, where they come from, how they are produced, and so on. This data comes from your suppliers and also your own bill of materials list of your product. For the manufacturing stage, you will need to know how the materials are processed, the quantity, the energy mix that is used during production, the waste, and so on. If you have in-house production, this data may be available to you, and you can also make direct assessments. If you're outsourcing, then you need to work closely with your supplier to get this data. It's also important to know how and also how far the materials, parts, and your products are transported in your supply chain. Collecting this information is the main task when performing the lifecycle assessment. The quality of the data is very important, as the LCA results are only as reliable as the data that is behind them. The data you measure directly is called primary data, and that is usually very high quality because it is specific to your product system. It could be the energy used for your production or your product-specific information, for example. This is very important to prioritize for the foreground system, as it is unique to your product and will then give a result that is more specific to your specific product system. Sometimes primary data is not available, or it's too time-consuming or expensive to obtain, and this is where secondary data is often used as a proxy. Databases such as Equinvent provide data on a lot of processes, such as steel production, that can be used to model your product system. The database data is often used for the background processes that are so generic that the database is likely to be representative of your product system. It can be used to fill out any gaps when modeling your foreground system, but the processes in the database are unlikely to reflect your specific impacts for production, which means that the results will not be as precise. Often, LCAs are made on existing products that have finished the development process, and therefore you have to recollect a lot of the data that you found during the process when you do the LCA. And even when you have the data, it's also too late to inform any decisions that are made in the development without making very large changes, as the decisions were already made previously. If we take a look at the product development process from scoping through development to implementation, there are a lot of potential to integrate LCA into the different phases of this development process. As the development project is scoped, so could the LCA be? What do we want to assess? What data will we need to collect as we go? This could be based on the sustainability requirements, the sustainability strategy, or even a hotspot assessment of a previous product. During the concept phase, the concept could be made based on predefined sustainability principles, as well as early calculations for decision-making in the concept phase. Once the design is detailed, the materials and supply selection could be informed by these initial LCA scenarios, and the information on materials, amount of materials, sourcing of these materials, and also the design lifetime of the product could all be output to this LCA data. During the production, data is collected from on-site measurements, such as energy consumption or waste generation, which is also input into the lifecycle assessment. By having the data collection in mind when developing the product, you ensure that the development team makes informed decisions, as well as gather the data needed for LCA, so it's readily available when you need it for the final reporting of the LCA study. As an example of working with data during the production process, it could be implementing IoT sensors that monitor and collect data on the production machines. It could be feeding large amounts of data into platforms and analyze it using machine learning or AI. This will enable you to identify hidden hotspots and also highlight which production variables most strongly influence your environmental metrics. The lifecycle assessment gives us an insight into the environmental performance of the product being assessed, but this is only the first step. If we stop the process here, the LCA is only used for documentation, and a lot of potential value is lost here. At this point in the process, you have unique insights into how you can improve the environmental performance of your product. The LCA can be used as input when doing a product assessment to identify improvement areas in the environmental performance of your product. It tells you where the largest impacts are in your product lifecycle, also called hotspots, and the most effective areas to focus on to improve the performance and reduce the impacts. The next step after the LCA is to identify specific opportunities for improvement and create these improvement scenarios. What would it look like if we improved the repairability of our product? What if we improved our recycling percentage or used recycled plastics? And then you need to run these scenarios in the LCA software to identify how much the improvement actually is, to quantify it, and also if there are any trade-offs to be aware of. These findings are then presented to the relevant stakeholders to inform the decisions in the new and hopefully improved design. So let's take an example of a simple hotspot analysis. In this example, we have a hotspot analysis of a generic industrial motor. If we look at the largest contributors to the carbon footprint by module, they are the motor housing, the stator, and also the rotor. Minimizing any of these, even by 10%, would decrease the overall impact by a lot more than focusing on, for example, the plastic in the terminal box and the top of the product. If we zoom into this motor housing, we'll see that the largest contribution to the motor housing module impact comes from the production of the aluminium. This shows us that the aluminium that we source is actually a hotspot in this example. So by choosing aluminium produced in Europe or even Scandinavia, where the energy mix might have a larger fraction of renewable energy, this contribution from the aluminium sourcing can be reduced significantly. This is one potential scenario. Once we know the hotspots, we can identify even more improvement scenarios. If you saw the last webinar on sustainability in product development, you may remember this figure, which is an adaptation of the butterfly diagram by the Ellen MacArthur Foundation. It shows the product lifecycle we saw in the beginning with all the lifecycle stages. It also shows the circularity approaches such as repair, remanufacturing, and recycling. This is the lifecycle perspective that we talked about earlier, taking into account all stages of the product lifecycle from the source and type of materials to the product, the use, and disposal of the product. We can look to each stage to identify how we might improve the impacts as well as any circular opportunities. A framework of strategies for improving product sustainability that we presented in the previous webinar is the Reduce, Extend, Recycle, also called Reduce, Reuse, Recycle framework. This is very useful to generate ideas for the improvement of sustainability in your product. Can you reduce the impacts coming from the sourcing of materials by, for example, selecting an alternative material or supplier? Can you extend the useful lifetime of your product through, for example, repair? Or can you prevent your product from becoming waste by, for example, recycling it into new products? In our industrial motor example, it could look like this: looking for aluminium with a lower carbon footprint, designing the product to be repaired in case of failure, and using recyclable materials that are separable so we can recycle it. Sometimes there will be trade-offs between these three strategies. Is it better to use a very durable material that will last 3 years longer but is not recyclable? Or is it better to use a recyclable material if it has a higher carbon footprint? That's why it's important to create these scenarios, measure them, and make informed decisions. So how do you get started with life cycle assessments? Hopefully, you now understand the basics of life cycle assessments and what you can use them for. This is the first step. The next steps include deciding on whether you want to do LCAs internally or if you want to have it done externally. Some customers prefer that it is handled 100% externally and only want the insights from the LCA to use, while other customers want a very collaborative approach where we work closely together and even play a supporting role to the internal team. If you decide on doing it internally, you need to add the right competencies to your team, which I will get back to in a moment. Then you need to choose your first LCA project. This is often driven by, for example, your sustainability strategy or a customer asking you for a carbon footprint of your product. If you want to do it internally, you need to set up your LCA software and databases to use and begin conducting your first LCA. As you go, you will extend the knowledge of your team if relevant and scale up based on your experience with the first LCA. The team to conduct an LCA could look like a project manager handling the time plan, the risks, and also the stakeholders, sustainability experts having the environmental perspective, data analysts handling the data, technical experts who have technical insights, and a supply chain expert who is doing the supplier contact and also mapping processes within your supply chain. In your team, you also need to have training in this LCA methodology. You need to have any LCA software and databases, as well as a review process to ensure the quality of your LCAs internally. This was it for our Operationalizing Lifecycle Assessment webinar. I hope it has provided you with an insight into the lifecycle assessment methodology and how it can be used to inform the product development process. Remember to sign up for more webinars on product sustainability, and if you have any questions, please reach out here on the Cladis website. We're here to support you in your transition towards a more sustainable future.